So, good morning, everyone. Today, with the last topic of the lecture, so we'll talk about the deep structure of the proton. And it's basically applying what we've started to discuss yesterday, factorization, and now the consequences evolution. So we can look at evolution equations quite generally in QCD, and then apply it here to proton evolution in the proton. So very generally, QCD evolution formulates the dependence of a cross-section for some observable on a momentum transfer. Huh? And as we've discussed yesterday, deep elastic scattering structure functions are a classic example where you have the scaling violations. And whenever we do factorization, we introduce some factorization scale, which is a priori not fixed, so it is arbitrary, and it means a physical cross-section cannot depend on this factorization scale. Huh? So we have here on the left-hand side, we have a physical cross-section. It depends on some hard momentum scale Q. And on the right-hand side, we have our factorized expression where we have a cross-section which we calculate in perturbation theory, and then we have some function f which depends on, say, long-distance physics, non-perturbative things, and we've separated off these degrees of freedom with a factorization scale mu. So think of f for DIS, think of f as being a Poisson distribution. For hadron collider cross-section, think of it as the convoluted Poisson luminosity. The important point is that the left-hand side doesn't depend on mu, the right-hand side does depend on mu. So you can take a derivative of the physical cross-section with respect to this factorization scale mu, and the right-hand side has to vary, that has to vanish, and that gives you two evolution equations. The one is for your non-perturbative function, say the Poisson distribution function. You can write down a differential equation, how f changes with the factorization scale. And so for this to be true, you can identify some evolution kernel, let's call it P, multiplying this function f. And for the hard perturbative cross-section, which is calculable in perturbation theory, evolution equation tells you you have to find the same evolution kernel P convoluted in the hard photonic cross-section. And so if you combine these two equations, then you see that this equation up here of the factorization scale independence of the physical cross-section is fulfilled. So in this way, quite on general grounds, you directly see how from factorization you derive any evolution equation, and in particular here for this case, if we apply to Poisson distribution functions, we derive the evolution equation for PDFs. But the same type of reasoning also holds when you do factorization. For instance, in soft and collinear dynamics, you set up an effective theory for soft and collinear, for treating soft and collinear emissions. You factorize your cross-section into certain functions. You derive evolution equations, and the same reasoning holds that when you start factorizing a quantity which does not depend on the scale which you choose to factorize it, then there are evolution equations coming from the self-consistency, right? Okay, so this is the basic picture, and here for PDF evolution, these splitting functions are calculable in perturbation theory. And I've given you some examples in the lectures on Tuesday and yesterday. So let's go back to see how this picture applies, I say, to mass factorization in the Drell-Yan process, where we've yesterday calculated the analog QCD corrections to the bare cross-section of QQ bar annihilation into a gauge boson. So we had seen that this is alpha S over 4 pi. Then in dimensional regularization, this is mu squared over the gauge boson mass squared to the power epsilon, and then we have twice the splitting function, the leading order QQ splitting function left with a 1 over epsilon singularity, so collinear singularity for gluon emission from both incoming quark and antiquark, and then our finite cross-section. Then we said, okay, we have to regularize or do the mass factorization, and that means we redefine our bare parton quark densities in terms of renormalized ones, which now acquire some scale dependence, and we subtract basically the collinear divergence here, the 1 over epsilon pole, with a splitting function, right? Then now this is our definition for the renormalized parton distribution function. So we can turn it around and say, okay, the bare parton distribution functions, they don't depend on the scale, so we can basically do d log mu f differential on this bare quantity, which doesn't depend on the scale. It has to vanish. And working out the derivative on this expression here, you immediately see that you get an evolution equation for the renormalized quark parton distribution function at leading order, which is then giving you the scale dependence. So it's the leading order QQ splitting function dotted into convoluted with the renormalized quark distribution, and then both, convolution product evaluated at the scale x, and both quantities evaluated at the scale mu f. So this is then how you actually derive such an expression starting from general considerations for this particular example that we went through. And so this is the simplest evolution equation that you have then for parton evolution in QCD. Huh? Okay, and basically the same procedure holds for any other collinear emission. So we can basically generalize this also to other emissions, and this gives you in total 4 types of different parton-to-parton splittings. So we had, so these are sketches for the processes for Feynman diagrams at leading order. So the QQ splitting function that we've just discussed comes from the emission of a gluon from an incoming quark, where you look at the outgoing quark to carry x times the incoming quark's momentum. Yeah? So this is basically giving the x dependence here. Now you can turn this around and you can also ask yourself, okay, let's look at an incoming gluon. And then let's look at how this converts into an outgoing quark, which carries the momentum fraction x of the incoming gluon momentum. And this is giving you the gluon to quark splitting function. Yeah? So this index QG, we read it from right to left. So this is the gluon to quark splitting. And likewise, we have a quark to gluon splitting, the PGQ splitting function. So at leading order, this diagram sketches is given here. An incoming quark then is converted into a gluon, which carries the momentum fraction x of the incoming quark's momentum. And then finally, we also have, due to the self-interaction of the gluons in QCD, we also have the conversion of a gluon into a gluon under radiation of a gluon, when this outgoing gluon here carries x times the momentum of the incoming gluon. Huh? So in this way, we can then derive universal quantities for all of these splitting processes. And this is giving us the complete set of splitting functions. And now, since we have this parton-to-parton conversion, so quarks going into gluons, gluons going into quarks, we actually have to set up a matrix equation for the evolution. So the evolution equation is now, this is basically a matrix here. The splitting functions form a matrix, 2 by 2 matrix, for where the index runs over quarks and gluons. And here for the PDFs, you have quark and gluon PDFs. So you have also mixing into each other. And then those evolution kernels, the splitting functions, we have calculated the leading order quantity for quark going to quark, but with similar considerations as we we went through in the lectures yesterday and on Tuesday. You can also then derive the leading order expressions for all these other splitting functions here from looking at the suitable collinear emission processes. And as I said, yeah, they are calculable in perturbation theory. And perturbative expansion alpha s at the moment goes up to alpha s cubed. So the first three terms are known, which is n in a row. This is now the standard approximation used for collider phenomenology at the LHC. And the for loop quantities here, this is currently work in progress and active area of research.
So usually we take in the splitting function as we saw, like here also, a real emission. So there can be a virtual loop also, right? Let's say Q going to Q, there can be a gluon loop, but it still be a splitting function of Q going to Q, right?
So these diagrams here, they are meant to be sketches, okay? So it's not like you take this diagram and you do the full calculation. If you go back to yesterday's lecture, for example, and you see in order to derive the leading order QQ splitting function, you actually had to consider all the emission processes and then combine everything, including the loop correction, which then gives you the delta function contribution here in the splitting function. So you have to write down a complete set of Feynman diagrams. This is just to illustrate basically the collinear momentum approximation, these diagrams here. Yeah?
Thank you.
So let's say for the QD splitting function, so similarly I can actually expand this splitting function P as the function of alpha E, let's say.
In QED?
QED.
Okay.
And then let's say if I want to calculate mixed electroweak QCD correction at two loop, then those splitting functions are just multiplicative, or there are some other structure will be prominent.
So if you want to have a combined QED QCD evolution, then okay, you would be adding the photon, for example. So this would be the first thing to do, and then this expansion here would be a combined expansion in alpha S and alpha electromagnetic. Yeah? I mean, like you typically do when you also include electroweak corrections. So this is then a combined expansion, and then, of course, you have to you have QED evolution. You have, for instance, a quark going into a quark under radiation of a photon. And likewise, you can have a photon splitting into QQ bar pair. So you have these type of splitting functions also at leading order. And then at some point, you will have to consider also mixtures, yes. So you will have to consider QCD, QED mixtures at higher loops.
So in this expansion, when you write this P as alpha P0 alpha square P1, in the same fashion, if I do purely electroweak or QD corrections, in the same fashion, let's say there will be some P prime of alpha E alpha square.
Right.
But those, my question is that for the mixed electroweak QCD corrections, those P's will come as the multiplicative way, or those P's will be the different P one has to compute.
I mean, in principle, QED radiation is a different process, so you'll have to compute them again. You can derive them from the QCD quantities, for example, by adjusting the color factors accordingly. So there is a way of actually breaking down or reducing QCD to a U1 gauge theory by adjusting all the color factors. So this is possible. It requires a little bit of care, but you can do it, yeah. Okay. Good. And right. So the name of splitting function basically comes from this parton to parton splitting.
Excuse me. So one more question.
Okay.
So like let's say in the first this splitting function. So if you have second order like their gluon can be two more gluon. So I just wanted to ask like P of QG like P of Qg at second order can be written as like P of Qq at first order multiplied by P of Qg at first order. Like it can be done or not. Like at the second order, it is actually not equal to. But my question is why they are not equal to basically.
So basically, if you solve this evolution equation here, in iteration, order by order, and perturbation theory, then you will see that this multiplicative appearance of two leading order quantities at the next to leading order is actually encoded here in this multiplicative solution. So if you write down this equation here and you plug in for this matrix its perturbative expansion, and then you write down the orders that you have in the perturbative expansion, and you see at the two-loop level you will have the product of two one-loop matrices, and then this is precisely the combination of any of these quantities in the respective entry of this matrix. So
No,
this
there is like in that if you put that expansion, there will be P of QQ at the second order genuine one.
and there will be a genuine one also at the second order, which you
So-
then have to calculate, which then includes all the loop corrections, say to whatever to this process here, like not just the double real emission, but also then loop corrections here and genuine two-loop quantities.
Okay.
Yeah.
Okay. Thank you. Thank you.
Just I don't have a two-loop example because this is basic. Two-loop is advanced. Two-loop is a PhD project. Okay? Good. Right. So in order to give you all the details, when we do this evolution, when we write down this evolution equation for Portland distributions, then we have a complete set of splitting function is written as follows. So we have NF fermions, NF is the number of flavors in QCD, so we have two NF minus 1 scalar equations, which are there for the evolution of non-singlet quantities. And then for the quark and the gluon mixing, we have a 2x2 matrix equation, which we just already discussed. So in a non-singlet case, you can define from the up and down and strange flavors, you can define in total 3 different quantities, which are the so-called flavor asymmetries. So this is the sum of quark flavors, quark and up quark distributions, and you take either the sum or the difference of the up and the anti of the quark and the anti-quark, and you take the flavor asymmetries between different quark flavors. So this could be up and anti-up, minus down, anti-down, combinations like this. These are the flavor asymmetries, and they don't mix with the gluon because any gluonic contribution would cancel out in this difference here. So they are only evolving with the so-called non-singlet splitting functions, and depending on how you combine the quark and the anti-quark, you either have a P plus or P minus splitting function in this non-singlet case. Yeah, so this is then, they also have individual evolution kernels. At the leading order, this is all the same, but at higher orders, they start to differ. Then another non-singlet quantity is the total valence distribution. So you take the difference of the quark minus the anti-quark PDF, and you sum over all flavors that you have in your theory. It's called a total valence distribution. Again, any gluonic contribution would cancel out in the difference here. And so this total valence distribution is then the sum of the P minus splitting function, which you already have here for the flavor asymmetries, plus another singlet part here in the non-singlet situation. And then you can sum over quark and anti-quark PDFs for all flavors in your theory. So up plus anti, up down plus anti-down, you sum over everything. This is the so-called quark flavor singlet distribution, and this one, due to the sum of quark and anti-quarks, this now mixes with a gluon, and this is the quantity which then goes into this vector two-dimensional vector of PDFs here, quark singlet and gluon distribution, which then goes into this matrix equation, and those two distributions, they mix with each other. And in the singlet sector, the complete expression for the matrix is the PQQ splitting function, and this is composed of the P plus non-singlet splitting function and another pure singlet contribution here, and then we have the gluon to quark, quark to gluon, and gluon to gluon splitting functions, which complete this two-dimensional matrix. So there is a lot of quantities, but you can all calculate them in QCD, and once you have them, then you can basically evolve any quark flavor combination that you like to have in your proton. Huh? Right, and in the end, it's solving numerically. It's solving a simple differential equation with respect to the scale. So what happens if you're now interested in in the shape of your pattern distributions at a certain scale? You start off with say a valence distribution, or a quark C distribution, or a gluon distribution at some low scale Q squared here. And so the valence distribution here, this has a bump somewhere here around 1/3. So this is the reminiscence of this leading order quark pattern model, where you say, okay, the proton is composed out of 3 quarks, and each carries 1/3 of the momentum fraction. So this is smeared out here a little bit in real life. But this is how you can understand this bump. And then you have the C quarks, where you have the sum over all the flavors, and then the gluon. And then this would be the initial condition, and then the solution of this evolution equation then would tell you how this initial condition is now being moved to higher scales. So if you go, say, to Q squared of 10 to the 4 GeV squared, say the scale of the production of a Higgs boson or double Z boson at the LHC roughly, then you see how the pattern distributions change. So the gluon rises steeply. The C quarks also rise a little bit, and the valence quark, they are basically being flattened out and roughly stay the same. Yeah? So this is then what you get in the end as a prediction from this evolution equation, provided you know some input at some boundary. Right. So this is what you get. Question is, how do you solve this differential equation? So in the old times, differential equations could be solved, for instance, by, since this is a logarithmic differential equation, you can basically rewrite it in a clever way, and then you can solve it with a slide ruler, essentially. Now, when I talk to undergraduate students nowadays, and I ask them, what is a slide ruler? Then most of them have never heard this or seen this. So the question is, can you still operate a slide ruler? If yes, then you can go to the library and you pick this volume of Physics Letters B from the 1980s, and you tear out the pages and you cut it out, and then you can assemble a slide ruler, and that allows you to actually compute the evolution of the quark and the gluon PDF to some approximation, which is, I would say, good enough for a back-of-the-envelope calculation. So that slide ruler actually comes with a calibration that contains initial conditions. But nowadays, we like to use modern tools, and so if you are interested in knowledge about the pattern distribution, and you would like to have also the evolution equation already solved for you, then you consult the LHA PDF database here, where you can download grids which contain the momentum distribution of all quarks or gluons as a result of fits of those PDF sets from various collaborations like ours or CTEC or MSHD NNPDF. And the nice thing is that now this has been developed into a standardized interface, so that it actually can be easily integrated in either Monte Carlo generators, or you can interface it easily to your own computer programs. And it also comes with I would say, quite good documentation. Right, so these are the modern tools in case you fancy them more. Okay, so this is about the theory framework. Now, how do we actually determine the Poisson content of the proton? So we basically nowadays take data from the Large Hadron Collider. This is aerial view of Geneva. And for what concerns us, in order to understand the Poisson content of the proton, we just need to look at the Poisson kinematics plane of the Large Hadron Collider. And this is giving you on the horizontal axis the Poisson momentum fractions x that you're probing in a proton. So basically the resolution of your proton, and then on the vertical axis you have the hard scale Q squared of your process. And then you have to read this diagram. This diagram is the Poisson kinematics plane for the LHC at 13 TeV. And then you have to read it as such. So this blue wedge is the Poisson kinematics of the LHC. Now you have to read it as follows. You're asking yourself, what kind of Poisson kinematics am I sensitive to when I look at the production of a particle of a mass, say, of 100 GeV, somewhere at central rapidity in my detector. And so then you go to this 100 GeV line here, and you look at those dashed lines, and then those tilted dashed lines here, they are denoting the rapidity, either plus or minus or central rapidity. So that just tells you that, say, Higgs boson production at central rapidity at the LHC is sensitive to Poisson dynamics somewhere around 10 to the minus 3, 10 to the minus 2, somewhere in this range here. Right. And if you want to do new physics searches, like,
so this plot particularly with respect to which pattern, like with respect to which pattern, this plot?
This is general. This is just kinematics. You have your basically what you're plotting here is we had this cross-section factorization yesterday for Hadron Collider cross-sections, where we have our Poisson luminosity and we have our perturbatively calculable cross-section. And then you're just looking for a given center of mass energy. You're looking at the Poisson luminosity, which is the kinematics which determine the Poisson luminosity here. So there is nothing special, because you can basically, the Poisson momentum fractions, they can be computed by a simple formula. So you're asking what's the mass of the final state that you're producing. You divide by the center of mass energy of the collider, and you multiply by either e to the plus or minus rapidity. This tells you where you are in your detector. And then this is to leading order. This is the Poisson kinematics. And so this is how you can basically read this plot here. This is also what determines you whether you are at central rapidity here or whether you are for lower mass final states, whether you are forward or backward outside your main detector.
So we know that the gluon pattern distribution function is very high compared to quarks. Still, those X regions are will be similar for the gluons for 100 TeVs and 0 reliability region.
The question, if you ask now for the quark or the gluon luminosity, and then the question is, what kind of process do you have in mind? If we have in mind Jalian production, where we are initially driven by quark-antiquark, then we are basically looking at the quark. We're predominantly looking at the quark luminosity in that X range here. If we look at ATLAS or CMS data, if we look at LHCb data, then they also measure at forward rapidities. So we are also looking here at 10 to the minus 4 and close to 1 X values. And if we are looking, for instance, at Higgs boson production in gluon-gluon fusion, which is driven by the gluon luminosity, then we'd be looking here at the gluon luminosity in an X range of, say, 5 times 10 to the minus 3, yeah, predominantly. So this is what this plot tells you.
Thanks.
Okay. Right, and then it also tells you that what I just wanted to say, if you're doing new physics searches, like you're looking for new particles with a mass of 1 TeV or even larger, then you're probing the region of large parton momentum fractions up here, where PDFs are typically becoming smaller, so you're then slowly squeezing yourself into the edge of phase space up here, and you're sensitive basically to that region. Yeah? Whereas if you look for light particles at the LHC, something like CHARM or so, then you have a low mass particle, and then it spreads all over the detector. Yeah? You can even go very forward. And then the question is, since we have our data at the LHC, we can use this data to extract the parton distribution functions, but we can also have data from other colliders, which have a similar kinematic coverage, and we can also use those data to determine the proton structure and then see whether things are compatible or not. And the available data from other colliders is from deep inelastic scattering. It had been done at the Hera collider, and this purple triangle here, this is the kinematics that had been probed by the Hera collider in DIS, and you see that it extends in coverage from X values of around 10 to the minus 4 up to X values close to 1, say 0.5. And then having data available in that X range at lower Q-squared values, we can still use this data to predict the parton luminosities at the LHC, because QCD evolution equation allows us to transport whatever we know at low scales to high scales. Yeah? So this is basically solving this evolution equation here, using whatever we fitted or what we determined as data at low scales. We can use it to then provide us with predictions at high scales. So this is why this overlap in kinematics is very important, because it's complementary measurements, it's complementary knowledge, and it allows us to also make predictions. And then down here at large X and low scales, there is also some older data that had been collected from fixed target DIS measurements, and this is still statistically relevant, because this is a large number of data points, so it's also included in such analysis. Now, with such parton kinematics plane, you can also assess the potential of future colliders. So we had been discussing briefly the electron-ion collider in the future. So now we can overlay the parton kinematics plane of the electron-ion collider here in this plot, and this is giving us this red triangle down here. This would be an electron-proton collider with a center of mass energy of 140 eV. You see that it covers largely the kinematics that already was accessible at Hera, but it'll certainly have much higher luminosity. It'll accumulate much more statistics, and it'll certainly also have better precision in the experimental measurements due to better detector capabilities. So that space down here in the future will be populated by new high precision data, which then also can be exploited in order to test whatever has been extracted at the LHC in order to have complementary tests. And then there are also now ongoing discussions. They are repeated every couple of years in this European strategy discussions for future collider projects at CERN. And so one of the future collider projects at CERN is a Large Hadron Electron Collider, which would basically be deep inelastic scattering inside the LHC tunnel. So you take out one proton ring and you put in an electron ring, and then you have in this whole ring with in the whole LHC ring with 27 kilometer circumference, you would have a gigantic deep elastic scattering collider. This is one of the plans that is being discussed. And the center of mass energy of such a collider would be 1.3 tera electron volt, roughly. Yeah? And then you can look at the kinematics plane of such a collider with a reach down to x values of, say, 10 to the minus 5, 10 to the minus 6 here. And so that would actually then be a collider where you can explore an entirely new regime of particle kinematics. So in one of the questions yesterday, we had discussed whether gluon saturation, for instance, at small x values plays an essential role or not. And so this is one of the physics cases. This is being put forward for such a collider. Huh? And this is just helping you to gauge the potential. Of course, you could also do other things. So you see with an electron-ion collider, with an hadron-electron collider of that size, you also explore. You can also explore high scales in the DIS processes. So you'd have a reach for searches for leptoquarks, for instance, up to a TeV, so things like that. There are many things you can do there. And then the flagship project or proposals at CERN is actually a gigantic circular collider, future circular collider, with, I think, current planning is like 90 kilometers circumference. So this would mean there is an entirely new tunnel to be built underneath CERN, and then in such a tunnel you can put in a hadron-hadron collider with a center of mass energy of 100 TeV. And just to put it into perspective, compared to the LHC with 13 TeV, this is the particle kinematics that you are probing at LHC 13 TeV, and then you really extend this significantly down to x values of 10 to the minus 6, 10 to the minus 7 at low scales here. And you also have a reach up to 10, 20 tera electron volt in direct new searches. So this is certainly, this would be giving us great options.
If FCCHH will give better constraint on gluon PDFs compared to LHC, it will probe lower in X.
Right. So the interesting thing is, if you look at what is currently known about the gluon PDFs at the LHC, we're sitting in X ranges a few times 10 to the minus 3, and if you're looking at a Higgs cross section, for instance, then you see we still have significant uncertainties. If you take the FCCHH and you're looking at Higgs standard model Higgs production, then somewhere your central detector would be sitting somewhere around here at 10 to the minus 4, and funny enough, the gluon is much better constrained there. So all the different determinations that we're looking at give us more compatible picture of the gluon. And certainly cross-section would also be much larger. So if you're a fan of standard model Higgs boson productions, then FCCHH would be giving you huge rates.
Okay.
But this is just, I mean, to understand the prospects for QCD measurements from such future colliders, and there regarding QCD. It's basically a question, what is the particle kinematics driving the reactions there?
Hi. In the previous plot, you had shown there are some overlapping regions from different sets of data from DIS, EIC. So how do people deal with such overlapping regions? I mean, do you also have to perform some kind of matching because you have two different input values at different scales, or what extra information?
This is a good question. So this just brings me to the next slide, and I wanted to explain you once how we are doing these PDF hits. It is basically you take all the so it's always determining these particle distribution functions. It's always an iterative cycle. So you have a set of data which you know is compatible to each other, meaning that you have a set of DIS data, you have some LHC data, and they all give you they're all compatible with each other in one FET. So there are no tensions, no significant tensions. And since these are different processes, like DIS down here, PP collisions down up there, there is also different theory involved, which a priori, they don't talk to each other except for the common input, which is parameters like alpha S, quark masses, and the PDFs. So you just have to make sure that the theory treatment for all these processes that you're fitting is accurate at a certain order of perturbation theory, and that the data set is compatible with each other. So this is what we are doing in this cycle. So we start off with compatible set of.
So compatible at the same scale, you mean? Like
well, they're living at different scales. So DIS data, for instance, we fit at low scales, and LHC data we fit at high scales. But we know how to connect these two scales with the evolution equation.
Okay.
So that tells you we basically make in practice we always make a fit ansatz at low scales, and then for DIS data we don't have to evolve so far, and for LHC data we have to evolve a bit further, and we see whether with such a common ansatz running the evolution we get a compatible result.
Okay, thank you.
Okay. If I have what? When we have, in a couple of years, when there will be EIC data, we'll be happily taking it along.
Yeah. So then one may consider like how the evolutions fitting is working. So if you have two low energy data, and if you want to evolve to the high energy data, and how they are actually at some scale, how they are matching.
I mean, this is what is happening right now. So basically, what goes into a fit is world data of deep elastic scattering data, and there is inclusive DIS data from HERA, and then also from previous experiments like BCDMS, NMC, and also from SLAC. They have been collected at different virtualities Q-skirts on different Q-skirt bins, and because of different center of mass energies, they also cover different regions of X, but typically they are sitting at low scales, and you make an ansatz for your PDFs, and then you run it up to whatever high scale you're interested in. And then there is also, say, semi-inclusive DIS for charm and bottom quark production, and there is Drell-Yan data from fixed target experiments. There is neutrino-nucleon DIS data, but then from the LHC, for example, there is W and Z boson production data. And this is sensitive to light flavor pattern distribution functions, up and down, a little bit strange. But this is also constrained by the DIS data, and so you have to see whether all this gives you a compatible fit of this whole set of data. And you have to see that there are no tensions.
Okay. So that means there are tension, or there is.
That means?
So my question is that do you see that they exactly match in the high energy scale, or there are some tensions?
They are compatible, otherwise we wouldn't be including them. Then we would say, okay, look, there is a data set and there is clear tension. And then you go back to the experiment list and you start to discuss with them what is causing the tension. So we've also seen this in the past. This data set here on DIS data, this is also not all the DIS experiments that have ever been conducted. So there is other DIS experiments that have been conducted where the data is simply has problems, and then you cannot include it. So you have to make choices, and you have to start from a good set of data, and then once you're sure that this works, then whenever there is a new data set, you check whether it is compatible with what you have already before, and then next question you ask yourself, is this new data set giving you any new information? Like is it giving you better constraints on what you had before, or is it just adding on top in a similar X range that you were probing anyway, and it doesn't have any better measurements, for instance. Yeah, so this is the next question, and then once these two items are checked and you have green light to go, then you can perform a new high precision determination of PDFs, but you should also keep correlations with the strong coupling constant and with the quark masses, because these are all correlated parameters that go into your prediction and that you have to account for. So fixing any of them and doing a singular fit typically leads you to a bias.
So how do I know that how much of it will go to the PDF fits and how much of it will go to the new physics, or let's say constraining alpha S and all these quark masses?
Or you basically fit all the parameters, and then you go through and you check whether you have reached an optimal value of your chi-squared. Yeah? So typically, I mean, the way it works for us is we start at a low scale with the evolution, so typically 3 GeV. This is a low scale for the evolution. And then we work in a scheme with 3 light flavors. Yeah? And in such a scheme, we make an ansatz for all the quark PDFs, like the valence and the C quarks, and the gluon PDF. And typically what you see is it's always a polynomial x to some power, and then 1 minus x to some other power. And then there is some, so this is giving you the endpoints, small x rise and large x suppression of the PDFs. And then there is some functional form of x which is flexible enough to allow for intermediate interpolation. Yeah, so we take it x to the power of some polynomial, which then again depends on x, yeah, with a couple of parameters. So if you count all the parameters here and you put in constraints from energy momentum conservation, then in total, including the quark masses and alpha S, we have of the order of 30 parameters. And this is enough to fit all this data.
So this polynomial is a matter of choice, or?
This is a matter of choice, and different collaborations who are fitting this have different approaches to parameterizing the functional form at the initial scale. But we find it is fully sufficient to have these polynomials with the order of 30 parameters. Yeah? Whenever we have a new data set that we are adding, then we can also extend this polynomial, like write down another parameter here, put it in, and then see whether during the fit this parameter is still compatible with the 0, or whether there is some new constraint on such a new parameter, so extending this parameterization. Yeah, this is a routine part of doing the fits there. Huh?
2 slides back when you drew these plots for Q square versus X. So what determines this lower line here? Like the
here?
triangle? Yeah.
This is just cutting it off at some point. In principle, you know, at the LHC, when they look at jet cross sections or at whatever Drell-Yan processes, they typically have a PT cut on the leptons and on the jets in order to cut down the rates. Otherwise, I mean, typical PT cuts on the leptons is like 20 GeV or so, and also cuts on the jets is, I think, a few tens of GeVs. Otherwise, the rates would simply be too high. Yeah? And also then the particle identification doesn't work so well.
If the detectors were better, then one would have got down a little bit.
If you, I mean, basically, if you're looking for specific final states, for instance, there is charm production data, for instance, which can also be collected by LHCb at low scales. Then you are at times really probing also that area here. But this is, I mean, I had to stop somewhere, so this is just 10 GeV, I think, is a good cut. If we are interested in the hard high-scale physics, yeah.
Thanks.
Okay, good. So this is the parameterization that we're using. We put it in. We simply run the evolution equation, and then we see whether we get a good fit. And the quality of the fit is then checked by looking at the chi-squared values. So typically, if you had done the math on the previous slide here, where I've listed all the data points, then we typically have of the order of 2,000 to 3,000 data points in a fit. Or you fit about 30 parameters, and then you keep all the correlations among the parameters, and then in the end, you get a covariance matrix for all the correlations, and you have to see that it remains positive definite. And then by looking at the fine print, then you can also look at the correlation, say, between alpha S, which is the fourth line from the bottom, and some parameters determining the gluon PDFs here. So then at times you see larger correlations. In other cases, you see that things are not so much correlated, but you basically also have an idea on potential pulls among or relations among those parameters. Yeah. So this is what we get, and finally, then you can plot results for those pattern distribution functions. Typically nowadays it is standard to plot them also with uncertainties, because experimental data comes with uncertainties, and we propagate these experimental uncertainties on the data through the fit in order to give then to illustrate the consequence of the experimental uncertainties on the resulting PDF fit. And this is why you typically see for all these pattern distribution functions, you see some bands. There is a central value, but then there is a band which is basically giving you a 1 sigma uncertainty band derived from the uncertainty, from the experimental uncertainties on the input data. Yeah? So this plot here in the upper left is the gluon distribution as a function of x from going into small x. So you basically see a rise, and this is at the scale of the Z boson mass. So you see it's steeply rising on the right-hand side. This is the gluon distribution normalized to our ABM fit, ABMP fit. This is just to illustrate the uncertainty. So you see that for x values, say 10 to the minus 2, down to smaller x values, you have uncertainty of a few percent. And if you go to larger x values, where generally the PDFs are suppressed because they're proportional to this 1 minus x factor, you typically see larger uncertainties. And this is one of the problems if you do new physics searches at the edge of phase space up here. You're sensitive to PDFs at large x. They come with some significant uncertainties, and so this is then sometimes a problem for precision predictions of the cross-section there. So are you sure that it's just standard model, or is there new physics then being buried inside large PDF uncertainties, which simply come out of the fit because there is less constraints due to data. No? And then in this plot up here for the gluon in the upper right, we also compare to other predictions. These are older CTEC parameterizations, CTEC 14, NNPDF 3.0, or something from the British MMHT. And we see, for instance, for the gluon that we do differ for x values below 10 to the minus 2. We do differ compared to them by approximately 10%. And these differences in predictions, they also propagate then into differences for the Higgs boson cross-section, for instance. Because the Higgs boson cross-section is dominated by the gluon PDF in that range over here. And then depending on what type of result you use for the pattern luminosity, you get significantly different values for the Higgs boson cross-section here. So that's an issue to be settled. Of course, all of these collaborations, they claim they're doing it correctly. No? But if the results differ, then only one of the results can be right. And so this is part of active discussion to highlight the differences which go into these different fits. Yeah, down here, this is the gluon. This is again the gluon PDF illustrated at large x here, And on the lower right, this is the normalized gluon distribution. So you simply see that if you go above x values of 10 to the minus of 0.5 roughly, then depending on which type of PDF you're choosing, for instance, NNPDF, you lose all predictivity. Yeah? So this is basically a question of further investigation there, and also a question of how can you reliably assess then PDF uncertainties outside a range which has been covered by data. No? Okay, so in order to extend this further and to incorporate new data into those PDF fits, we have recently looked at top quark cross-section data. So the top quark cross-section can be calculated in a similar approach with our standard QCD factorization formula. The hard perturbative cross-section is now known to NNLO, which means leading order NNLO approximation. So this is giving us quite good theoretical accuracy. It depends on the top quark mass and on the strong coupling constant, and predominantly on the gluon PDF. And the effective Poudon X values that you're covering here is, say, roughly 2 times the top quark mass divided by the center of mass energy, which is X values of 2.5 to 5 times 10 to the minus 2. So it is in a similar range as those Poudon dynamics that are also driving the Higgs production cross-section. So it's an interesting question to see how is the top quark, how can the top quark data be described, and is this giving us some new information about the gluon PDF? If you do the top quark mass fit here, then there's also the choice of the scheme. You can do the top quark in the pole mass scheme, in the on-shell scheme, or you can do it in a running mass scheme. There is a certain sensitivity of the cross-section to the top quark mass, which helps you in order to constrain the top quark mass, so you get quite precise numbers. And in order just to see what's the added value of new data, new high precision data from the LHC, both from Atlas and CMS, and they have now, on top of total cross-sections that were published in the past, they have now highly precise data on double differential distributions in the pair invariant mass of the top quark and in the pair rapidity of the top quark pair. And in total, this is of the order of more than 100 data points. So previously we only had inclusive top quark cross sections, which is about 10 data points, but now with say more than 100 new data points in the fit, there is a significant statistical information coming in and weight coming in, and then we can check how such data can be described by existing PDFs. And so here in a recent study, we took the ABM PDFs, we took a newer version of CTEC, MSHT, and NNPDF 4.0, and we were looking at the chi-squared values with and without PDF uncertainties. So the first number is always chi-squared values with PDF uncertainties, and you see that you typically get a good description. So we have 34 and 19 or 15 and 15. So typically we have chi-squared values around 1 here. And overall we have, for the ABM fit, we have 122 data points and chi-squared value of 101 with PDF uncertainties, or 117 without PDF uncertainty. So this is a really very good compatibility. If we look at other PDF fits, then we see that within PDF uncertainties, they're all compatible with the data, but if we just take the central value of those PDF fits, then we see the chi-squared is becoming much worse. For instance, for CT18, the chi-squared would be 337, so that just tells you that there is significant potential in those data if it is included also in fits of other groups in order to further constrain their PDF uncertainty here. And even for NNPDF, you see that once they typically claim they have a conservative approach to PDF uncertainties, so even they have quite a large potential in further reducing the uncertainties when they include such data. Yeah? Okay, and this is something which we conducted and we put out sometime last year, including this top quark data in an ABM PFIT, and there are some new sets, ABM PTT, which are available at LHA PDF. For us, the nice information was we could basically confirm our gluon PDFs in the X in the range of X values 10 to the minus 2. We could further reduce the uncertainties a little bit, and we basically get a good compatibility with what we had previously. So for us, it's a confirmation that with our PDF determination, we are on the right track. Fitting also coupling constants and the quark masses. The alpha S value which we derive is 0.1150 with an uncertainty of roughly 1 unit on the third digit. This is lower than what is typically being quoted as the world average. If you ask me over coffee, I have many comments on the world average, but I certainly do believe that our number is a correct value. But this is also subject to ongoing discussions with theory and experimental colleagues and also with PDG authors. So stay tuned for a lot of further fun here. This is just comparing our C-quark, U-quark, and D-quark PDFs with what we had previously. So you see within uncertainties, sometimes the uncertainties are a bit smaller with our new fit. But by and large, we basically have good compatibility.
Sorry, the value you quoted,
Yes.
For ABM PTT, so 0.1150, that number, it's a simultaneous fit of the PDF parameters and the alphas.
Right.
So when it's going towards lower values, from where there should be a likelihood pull, which is something you're analyzing when you're fitting the parameterization.
Right. So so basically alpha S is of course correlated with the gluon PDF. It is correlated with the top quark mass. These are the main sources of correlated parameters. Now, if you do a fit, and this has been done by say other collaborations, if you do a fit and you fix the top quark mass to a value say of 172.5 GeV, then this is bringing down the cross section, and you have to compensate by a larger value of alpha S. Yeah? So this is one of the pulls that we are seeing, and we've basically done those chi-squared scans, fixing, and then you see you move away from the optimum and you pay a price basically. So this is why we claim fixing any of these parameters to a particular value. This is just introducing a bias to your fit. And likewise, we've also done those studies where we say, okay, we fix, for instance, alpha S, and then we can see how the gluon PDF is moving, or we fix the top quark, and we also see how the gluon PDF is moving. So we have done these studies in the past, and they all confirm this picture that you do get a bias at the level, so 0.001 roughly uncertainty is the experimental uncertainty. And fixing those parameters, you do get biases at the level of 2 to 3 sigma. So this is outside the uncertainty range, is typically a consequence of the theory treatment that you're doing. And this is, I think, the message to take away. So the differences in those parameters that are being provided by different groups, this is really almost always a consequence of the theory assumptions and the theory treatment. And this is what we have to question there.
And if you set it to the on-shell mass of the top in your fitting.
Right. So we get a value for the pole mass of 170.2 GeV with an error of 700 MeV. This is the optimal value which we get out of the fit if we do this, if we set this to 172.5 GeV, for instance, like standard CMS or Atlas values that are chosen in the analysis, then we move away from the optimum. Yeah? Then we move towards larger alpha S values, and our gluon moves a little bit, but mostly alpha S.
Maybe it's a bit more technical, but when you make these different choices, the chi-square, do they just shift in, like the bottom of the chi-square shifts, or also the shape of the chi-square inflates to quote a total uncertainty?
It's basically you have a chi-squared parabola, and you move away from the minimum. You move away, and you acquire a penalty in your fitness. Right. Okay. So right. So this is just to say we have good compatibility. This is for the gluon finally. For the gluon PDFs, we see we have within uncertainties we agree between the old AVMP16 fit and the new fit, including topcock data. And for larger X values, we have a somewhat reduced uncertainty here. And we still see, with also comparing to new PDFs like CT18, MSHT20, and NNPDF 4.0, we do see differences still of the order of 5 to 10% for the gluon in the relevant X range. Here 10 to the minus 2, 10 to the minus 3, which is driving the Higgs cross-section at the LHC, meaning that with our gluon and our alpha S value, we typically get in the end a somewhat lower Higgs cross-section of the order of 5 to 7% lower than other people. Yeah, this is something to be looked at. So I think at the moment, as long as experimentalists are still fitting signal strength parameters in the Higgs cross-section area, the precision is not yet pushing the theory to the limits. But as soon as Higgs physics is also becoming precision physics, there will be certainly more pressure also on all these PDF determinations in order to resolve the discrepancy and to come to terms with this. But as we understand, the difference is a consequence. As I said, it's a difference of different theory assumptions that go into the fit. Well, basically they should, in the end, at x equal 1, they should all vanish, because from the probabilistic point of view, you should not have any parton carrying all the momentum of the proton. So they all vanish, but the speed at which they vanish, this is kind of giving you the different shapes there. And then the other question is basically assessment of the uncertainties here. So we would say our uncertainty here, is basically driven by, in the gluon PDF, by this 1 minus x parameter, and then you have one exponent, and then you determine an uncertainty range for this one exponent. And this is what we quote. Now you can argue with us whether you find this too aggressive, whether you should somehow enlarge this or not. This is a matter of debate, because at some point we're leaving the measured range, and then it's a question, how do you extrapolate into unmeasured region? And we say, okay, this is our functional form. We give an uncertainty on that parameter, and this is basically how we extrapolate, and this is determining our uncertainty. So take it or enlarge it by a factor of 2 if you like. I mean, this is also what we have been recommending for different new physics searches in order to be more conservative. Maybe enlarge it by a factor of 2 just to see how it affects your analysis. But this is generally the strategy that we would claim it should be done. Other groups like NNPDF, when they have this neural network approach, they're totally unconstrained. So for them, it's always blowing up. But then, what can you learn from this?
Beyond x equal to 1/3, we would assume that in the conventional picture, the gluon PDF should go to 0. Until unless there's new physics or.
Well, the gluon PDF should vanish, and data coverage ends around here roughly. So this is we go up to a few times 10 to the minus 1, and beyond this there is no data. You can see this from going back to this parting kinematics plane here, the LHC. So DIS data that the highest X bin is around X 0.3, 0.5. So this is where you really stop with DAS data. There are some fixed target experiments that have kinematic coverage up to X values of 0.8. But this is then mainly constraining light flavor PDFs. And then you have to see, okay, once you're really in a high mass regime beyond 1 TeV at the LHC, so if you're looking for, I don't know, Z prime boson or so, of a mass of 2 to 3 TeV, then you're really substantially affected by PDF uncertainties there. So this is why then, in such cases, we would recommend to experimentalists also to try to have a data-driven approach so that they make bins and invariant masses of lepton final states, for instance, and then they try to cross-calibrate also from data. Okay, good. So basically that's all I wanted to say. So the summary is brief. I tried to convey to you the idea of Portland evolution, and I've illustrated to you how the evolution equations can be directly derived from the Dural-Jan cross-section, for instance, that we calculated yesterday, or similarly from the DS cross-sections. So you can just go back to those slides. You do the differential with respect to a factorization scale, and then there you go with the evolution equations. And then for assessing the physics potential of hadron colliders, personally I find those Portland kinematics planes a useful tool because it quickly allows you to see what are the relevant kinematic regions. And for precision studies of hadron structure, we do need, first of all, we do need high precision experimental data, and then this should be subject to a dedicated analysis, and it's important in all analysis to keep correlations with PDFs, alpha S, and quark mass parameters. And in working with experimentalists, we also try always to encourage them to keep all those correlations in some analysis when they, I don't know, so for instance, imagine they try to fit some SMEFT couplings for new operators that parameterize some new physics interactions, and they want to derive some bounds, then it's also good, especially in the high TeV region, to actually account for all the uncertainties that you already have in a standard model. And finally, from active research, from our PDF fit, we believe we get a good confirmation of our gluon and also confirmation of our Higgs cross-section numbers then. Thank you very much.
Thanks, Sven, for this exciting set of lectures and questions.
Thank you. So, will there be any fragmentation function by AMPS?
So from our side, we haven't looked at fragmentation functions yet. So
Polarized PDFs.
Polarized PDFs might be something we can start looking at. Problem is that the data on polarized hadron scattering is still scarce. So it's mainly RIC data in a limited energy range, in a limited kinematics range. And there has been in the past some data from the Hermes experiment at Hera, but this was fixed target at low scales, and they don't have a big reach in X and Q squared. So this is why we didn't look into this. But it's certainly something which we have in mind. It's just it's always a question of priorities and manpower.
Thank you.
So, can you go to slide number 6?
6. Six here, okay?
So that non-singlet, shouldn't it be NF minus 1 instead of 2NF minus 1?
NF minus, I think if you call, so I came up with 2NF minus 1 because I'm calculating quark and antiquark separately. Yeah?
Okay.
So I have quark and antiquark, I count them separately, and then the minus 1 is basically subtracting the flavor singlet here. So this is then the one which you take out, and it talks to the gluon, and all the others are in principle flavor non-singlet. distributions where you have separate access to all the quark flavors. And then conventionally what is being, if you look at the flavor symmetries, then those three flavor symmetries and the valence distributions, those are the ones that are typically considered.
Then it should be, I think, then 2NF minus 2 instead of 2NF minus 1. Like quark and anti-quark. That one should not, like.
I don't see this, but
Okay.
you can explain it to me on the board, okay?
Okay, thank you.